Water, it is the lifeblood of our planet. Without it, Earth would be a barren, desolate rock. Life in all its magnificent diversity depends utterly on this simple yet extraordinary molecule. Its presence is what defines our world, setting it apart in the cosmic neighborhood. From the smallest unseen microbe to the colossal whale navigating the deep, all living things are intrinsically tethered to water. It tirelessly shapes our landscapes, dictates our climate, and indeed, underpins our very existence. This molecule, H2O, is a true cosmic marvel, an architect of biology and the patient sculptor of geology across eons. Consider its profound and irreplaceable role in the grand unfolding story of Earth. Look at our home, Earth, as if from the distant vantage point of space. What do you see? You observe a vibrant, swirling blue sphere, a beacon of life in the void. This striking azure hue is the unmistakable signature of water. It covers the majority of our planet's surface, a shimmering, dynamic veil. It fills the vast, deep basins of the oceans. It gleams brightly in the expansive polar ice caps. It flows with purpose in mighty rivers that carve through continents. It even hides in immense quantities beneath the ground, a hidden reservoir of life. And it floats serenely in our atmosphere, forming clouds and existing as invisible vapor. Water is truly everywhere, a constant, pervasive presence in our daily lives and planetary functions. So where is all this vital water located? The vast majority of it, an almost overwhelming proportion, resides within the salty embrace of the world's oceans. These immense saline bodies cradle the continents and drive global systems. Following the oceans, the next largest reservoirs are the frozen realms, the glaciers, ice sheets, and permanent snow cover. These icy expanses lock away substantial quantities of fresh water, primarily at the poles and in high mountain ranges. Beneath our very feet, extensive systems of groundwater fill subterranean aquifers. Surface freshwater found in lakes and rivers, while critically important for human societies and terrestrial ecosystems, represents a surprisingly small fraction of the total. Even the air above us holds water as vapor, a crucial player in our weather. Our planet Earth is remarkably special. It stands as a verdant water world in what appears to be a largely arid solar system. While other celestial bodies, planets and moons alike show evidence of ice and some even tantalizing hints of subsurface liquid oceans, Earth proudly boasts liquid water in astonishing abundance right on its surface. This unique characteristic is largely thanks to our planet's fortuitous Goldilocks position relative to our star, the Sun. We are not too hot nor too cold. Our orbital path provides conditions that are just right for water to exist predominantly in its liquid, life-sustaining form. This precious, life-giving resource is what makes Earth a dynamic, evolving and living planet. It is a cosmic oasis teeming with biodiversity and potential, all thanks to the remarkable properties of water. Let us now delve into the specific numbers, the grand accounting of Earth's water. The total inventory of water on our planet is truly immense, almost beyond comprehension. Approximately 97% of all this water is saline, contained within our sprawling oceans and seas. This vast, salty expanse is not merely a passive pool, it is a dynamic engine driving global weather patterns and ocean currents. It also supports an incredibly diverse biosphere, unique to its chemical makeup. The sheer volume is staggering, a liquid legacy of Earth's geological and atmospheric history. This overwhelming oceanic dominance fundamentally shapes our planet's climate and its intricate chemical balances. It powerfully underscores the predominantly salty nature of Earth's available water. What then of fresh water, the resource so critical for terrestrial life and human civilization? Astonishingly, only about 3% of Earth's total water is fresh. And the story deepens, for most of this fresh water is not readily accessible to us. A significant majority, roughly 68.7% of this freshwater, is locked away in glaciers and ice caps. These colossal frozen reservoirs are primarily located in the remote regions of Greenland and Antarctica, with smaller amounts in mountain glaciers. Another substantial portion, about 30.1% of all fresh water, exists as groundwater, concealed beneath the Earth's surface in aquifers. This leaves a remarkably tiny fraction, approximately 1.2%, as surface fresh water. This minute percentage includes all the lakes, rivers, swamps, and atmospheric water that we see and interact with most directly. Water, however, is never static. It is in constant, unceasing motion. This magnificent planet-spanning movement is described by the hydrological cycle, often called the water cycle. You can envision it as Earth's own intricate plumbing and purification system, operating on an immense planetary scale. This entire cycle is powered by the inexhaustible energy radiating from the sun. It is the sun's warmth that lifts water from the oceans into the atmosphere. The cycle then transports this water across the globe, from the atmosphere to the land, and then, inevitably, from the land back to the oceans. It is a continuous, dynamic, and self-renewing process. This perpetual journey has shaped the face of continents and sustained life for billions of years. The hydrological cycle commences with the process of evaporation. The sun's energy, its light and heat, bombards the surface of oceans, lakes, and rivers. This energy input causes liquid water to transform into water vapor, a gaseous state. This invisible vapor, being lighter than the surrounding air, rises gracefully into the atmosphere. Plants also play a crucial role in this atmospheric uplift through a process called transpiration. They absorb water from the soil through their roots, and then release water vapor from tiny pores in their leaves. Together, these two processes, evaporation and transpiration, are often combined and referred to as evapotranspiration. They represent the primary pathways by which water transitions from its liquid state on Earth's surface into the atmospheric phase of its grand, unending journey. Once aloft in the atmosphere, the water vapor embarks on an upward journey, encountering progressively cooler temperatures at higher altitudes. This cooling triggers the process of condensation. During condensation, the water vapor transforms back into tiny liquid water droplets, or if temperatures are cold enough, minute ice crystals. These microscopic particles then aggregate, gathering together to form clouds. Clouds, in their myriad forms, are the visible manifestations of water's remarkable atmospheric voyage. They are carried by winds, often across vast distances, effectively transporting water from one region of the planet to another. When these accumulated water droplets or ice crystals grow sufficiently large and heavy, gravity takes over, and precipitation occurs. This can be in the form of rain, snow, sleet, or hail, returning water from its atmospheric sojourn back to Earth's surface. When precipitation reaches the land, it follows several distinct pathways dictated by gravity, topography, and the nature of the surface itself. Some of this water flows over the land surface as runoff. This runoff collects in channels forming streams, which then merge into larger rivers, and may eventually fill lakes. Ultimately, a significant portion of this surface runoff finds its way back to the oceans, completing a major arc of the hydrological cycle. Another vital portion of the precipitated water seeps into the ground. This process is known as infiltration. Infiltrated water can replenish soil moisture, which is crucial for plant life. It can also percolate deeper into the earth, eventually reaching and recharging underground aquifers, thus becoming groundwater. All of Earth's water, in its myriad forms and locations, collectively constitutes what we call the hydrosphere. This comprehensive term includes the vast, deep oceans and the interconnected seas, the saline titans that dominate our planet's surface water inventory. It also encompasses all freshwater bodies, such as the expansive Great Lakes of North America and the countless smaller ponds and wetlands scattered across the continents. Rivers and streams, functioning as the arteries of the land masses, are also integral to the hydrosphere. They diligently carve landscapes over geological timescales and serve as critical conduits for transporting water, sediments, and nutrients. The hydrosphere is a complex, interconnected system, constantly interacting with the atmosphere, the lithosphere, Earth's solid crust, and the biosphere, all living organisms. Beyond these more familiar surface water bodies, the hydrosphere also includes the vast, often unseen realm of groundwater. This is the water stored within the pores and fractures of underground rock layers and sediments known as aquifers. The cryosphere, which encompasses all frozen water on Earth, is another crucial component. This includes the massive glaciers and continental ice sheets, as well as sea ice, permafrost, and seasonal snow cover. These frozen giants store enormous quantities of fresh water, influencing global sea levels and climate. Even the water vapor present in the atmosphere, though representing a relatively small percentage of the total water volume, is a vital part of the hydrosphere. Atmospheric water is essential for the formation of weather patterns and plays a key role in regulating Earth's climate system. Let us now plunge into the depths of the oceans, the very heart and soul of the global hydrosphere. Seawater is far more than just simple H2O. It is, in fact, a remarkably complex aqueous solution, teeming with dissolved salts and minerals. The primary measure of this inherent saltiness is a property called salinity. On average, global seawater possesses a salinity of approximately 3.5%. This percentage means that every kilogram, or liter, of seawater contains about 35 grams of various dissolved salts. This salinity is not perfectly uniform across all oceans. It varies subtly depending on geographic location. Factors such as rates of evaporation, levels of precipitation, inflow of fresh water from rivers, and the melting of ice can all influence local salinity levels. What exactly are these dissolved salts that give the ocean its characteristic taste and properties? Remarkably, just 6 major ions account for over 99% of all the dissolved solids in seawater. Chloride is the most abundant of these ions. Sodium is the second most plentiful. When these two ions combine, they form sodium chloride, which is ordinary table salt, the most well-known component of seawater saltiness. The other 4 major ions contributing significantly to ocean salinity are sulfate, magnesium, calcium, and potassium. These ions primarily originate from the slow weathering and erosion of rocks on land. They are then transported to the oceans by rivers over vast stretches of geological time. Volcanic activity occurring on the seafloor also contributes dissolved minerals directly to the water. Beyond these 6 major ionic constituents, seawater contains a veritable cocktail of other substances, often referred to as trace elements. Indeed, virtually every naturally occurring element on the periodic table can be found dissolved in seawater, although most are present in extremely tiny concentrations, measured in parts per million or even parts per billion. These trace elements include essential nutrients like nitrogen, phosphorus, and iron, which are absolutely vital for supporting marine ecosystems and the growth of phytoplankton, the base of the oceanic food web. Dissolved gases are also present in significant quantities. Oxygen, produced by marine photosynthesis and through exchange with the atmosphere, is crucial for the respiration of marine animals. Carbon dioxide is another critically important dissolved gas, playing a key role in ocean acidification and the global carbon cycle. Understanding Earth's water in all its facets is far more than a mere academic exercise or a pursuit of scientific curiosity. It is fundamentally a matter of our collective survival and responsible stewardship of this planet. The distribution of water dictates where life can flourish and where deserts prevail. The hydrological cycle is a fundamental planetary engine, connecting all components of the Earth system in an intricate dance of matter and energy. The chemistry of our vast oceans profoundly influences global climate, biodiversity, and the very air we breathe. As our planet faces unprecedented environmental changes, comprehending these intricate water systems becomes ever more critical. We must cultivate a deep appreciation for this precious, life-sustaining resource. We must strive to protect its delicate balance for the well-being of all future generations. The story of water is, in essence, the story of Earth itself, and it is inextricably our story too.